We're going to wait just a few minutes to get started to see if any more folks show up, and then we'll get going. Welcome, everyone. Welcome, everyone. Thank you for attending the webinar today. We're going to be talking about multi-metals continuous water analyzer that's based on energy dispersive X-ray fluorescence, and specifically its application to meeting power plant ELG or effluent limit guideline rules. We're going to talk a little bit about the current state of those effluent limitation guidelines for steam electric generating utilities. We're going to talk about the operation and capabilities of the Xact 920, which is the water analyzer based on X-ray fluorescence that we're talking about. And then we're going to go over some of the field testing that we've done with the Xact 920 monitoring selenium in bioreactor effluents. So with the ELG rule, currently compliance is required as soon as possible. The rule is actually promulgated at this point. Many plants will need to use bioreactor technology to achieve the new selenium limits. Daily measurements of selenium, arsenic, and mercury are required under the rule. And plants that are not removed from service or that are not in the voluntary incentives program must meet these new limits by December of 2025. If you're a voluntary incentives program plant, the rules and the limits are a little bit more stringent, but you have a little bit longer to meet them. You have to meet them by December of 2028. These are the limits that the rule has promulgated. I've highlighted selenium in particular, since this is the one that's particularly hard for facilities to achieve. Most facilities will have to meet a daily maximum effluent limit of 70 micrograms per liter or parts per billion, and a monthly average of about 29 parts per billion. Also, you have some rules for arsenic at about 18 parts per billion on a daily average, or daily max, excuse me. And if you're in the voluntary incentives program, like I said, you have a little bit longer to meet it, but your limits are a little bit lower as well. So one of the things that might come to mind with this is why you might want to monitor these pollutants in real time. And there are several advantages to monitoring pollution in real time. First of all, you can determine if a limit exceedance will take place before it actually does, which means you can have some time to react to it, change your treatment process, and hopefully prevent an exceedance from occurring in the first place. In the long run, it'll also allow for some feedback that will allow you to fine-tune your controls and be able to operate your treatment facility more efficiently, saving the power plant money. Also, it has some advantages in terms of minimizing human error in the process. There's a lot of steps in gathering a sample, sending it off to a lab. The lab has to do the analysis. There's lots of points in that process where human error can take place and lead to some erroneous results. It's also helpful that with this instrument, you can do inlet and outlet measurements from your selenium treatment from your bioreactor to determine your treatment efficiency. And you can see how effective the bioreactor is actually at removing selenium. This slide shows the Xact 920. The instrument can measure up to 65 different elements simultaneously, including many of the elements that are of concern in the ELG rule, like selenium, arsenic, and if you're in the VIP program, bromine. The instrument operates by spray drying the water sample onto a filter tape, and then the resulting filter tape deposit is analyzed by X-ray fluorescence. That allows for some pre-concentration to take place in the sampling process, giving us better detection limits. It builds on two technologies that have been developed and commercialized by Cooper Environmental. The ambient air XRF analyzer, which is the blue box that you see there in the picture. We have well over 200 of these instruments in the field. It's a very, very robust design and has been operating in a wide variety of conditions and also in a wide variety of geographic regions. It also builds on the quantitative aerosol generator, which was developed under the Electric Power Research Institute sponsorship for the calibration of PM SIMS. And that's where a lot of our spray drying technology for the water analyzer comes from. For those of you who may not be familiar with X-ray fluorescence, this slide shows a little bit about how X-ray fluorescence works. The picture there, you can see kind of a model of the atom where you have a nucleus at the center and you have electrons in various K, L, and M shells surrounding the nucleus. The incoming X-rays excite the atom and cause one of the inner shell electrons, either a K, L, or M shell electron, to be ejected from the atom. And then an electron from a higher energy level falls to fill in that vacancy, and that process releases energy in the form of a fluorescing X-ray. The energy or color, if you will, of that X-ray is characteristic of each individual element, and the intensity or brightness is proportional to the mass of each element. So that, in a nutshell, is how X-ray fluorescence works. Now, there are a number of advantages to X-ray fluorescence relative to other analytical techniques. XRF uses inner shell electron transitions so that the response is not dependent on what the atom is chemically bound to. In other words, iron will always appear as iron, regardless of whether it's iron sulfate, iron nitrate, iron chloride. It doesn't matter. The X-ray fluorescence, it will always show up as iron. You can measure a wide range of elements simultaneously with energy dispersive X-ray fluorescence. XRF is non-destructive, so some of these samples can be reanalyzed at a later date, either by X-ray fluorescence or a different analytical technique. XRF is very, very stable. Calibrations can last for years. For our ambient units, we have had units that have had the same calibration and been reading accurately for 4 or 5 years without needing to be recalibrated. And then finally, XRF response is linear over a wide range of concentrations, over 5 orders of magnitude. And what this means is if you have a lot of variability in your sample, it doesn't matter. You don't have to have a different calibration because your concentration is at a very high level or very low level. You can utilize the same concentration, or excuse me, the same calibration. These are some of the elements that can be measured by the Xact 920. Anything there that is highlighted in blue, from silicon all the way on up to uranium, can be measured by the Xact. We have circled some of the elements of interest there in yellow that are under the of interest based on the ELG rule. And also some other elements that might be of interest in terms of monitoring for corrosion products and things like that, like chrome, manganese, iron, are also circled and highlighted there. Those might be of interest in terms of monitoring for plant efficiencies in other areas. The instrument cannot measure mercury at this time because when the spray drying process occurs, mercury is most likely present in the form of a vapor, which cannot then be captured on the filter tape. So that's why we don't say that we can measure mercury at this time. These are some of the detection limits that are the instrument is capable of for key elements of interest there. 30-minute detection limits for most elements are less than a part per billion. It is important to remember, though, a couple things with the Xact and detection limits. A function of sampling time. So basically, the longer you sample for, the more pre-concentration you can get on the filter tape, and the better your detection limits are going to be. It's also a function to some degree of total dissolved solids. There's a limit to how much loading of salt that you can get onto the filter tape. And so if you have a sample that has high TDS, you're not able to actually get as much flow through the filter tape. And so that can make your detection limits a little bit poorer. And then this slide kind of shows you what I mean by that in terms of the detection limits being a function of total dissolved solids. You can see here we have the detection limits graphed on the y-axis and the total dissolved concentration on the x-axis. And as you increase the total dissolved solids, what you see is your detection limit increases or gets a little bit worse. This slide here shows a little bit about how the instrument operates. It's a schematic of it. You have, number one, you have your sample source there, and then we typically have a sample pre-treatment and transport system. We might call this like a fast sample loop. It flows at the rate of, say, maybe a liter a minute, and so that you can pull the instrument from your sampling location, pull the sample from the sampling location to the instrument much more quickly. And then depending on the type of sample that you have, you may have some pre-treatment, like some filters to get rid of suspended solids. If there's a lot of those, you may have a sterilizer to eliminate biologicals if you're sampling in, say, surface water or something like that. Once it leaves this sampling loop, step 2 there, goes into what we call our liquid blending module. And from that 1 liter a minute of sample from the fast sample loop, we actually pull about 1 milliliter per minute from that. And then the remainder goes back into the source. In the liquid blending module, which is the letter A here in red, we mix the sample with an internal standard. And then that mixture gets sent onto the drying chamber where it's spray dried. Much of that sample aerosol gets sampled onto the filter tape. That which is not is passed on to the carbon trap and through a flow meter pump and then exhausted. Once it's on the filter tape, that's where it gets sampled and then analyzed by X-ray fluorescence. This slide shows some of the kind of key parts of the instrument. We have the drying chamber, which is that silver cylinder in the upper left-hand corner. The blue box there contains our XRF analyzer as well as the tape drive. We have a main power panel. We have some controls for heaters, some controls for airflow, liquid blending module, and exhaust gas treatment. And then this kind of shows you what the inside of that blue cabinet looks like in terms of the tape drive. You have a reel-to-reel tape drive there. The filter tape travels from left to right. You have your sample dried aerosol from the drying chamber coming down through the inlet tube and onto the filter tape. The dried aerosol gets deposited onto the filter tape. And you sample for a period of time, typically a half hour or an hour. And then after sampling is complete, the aerosol is advanced, or excuse me, the deposit is advanced into the analysis area where it gets analyzed by X-ray fluorescence while the next sample is being collected. So you have a continuous sampling and analysis cycle that's ongoing. You have the sampling and then immediately followed by the analysis while the next sample is being collected. We also have a number of quality assurance features that are present on the instrument to validate the stability, particularly of the XRF system. The instrument is calibrated with thin film standards, and then typically we also do checks of the instrument with solutions to make sure that it's reading accurately before we ship it out to the field. And then with each sample, we have automatic checks of the stability of the X-ray fluorescence response. And in the analysis area underneath the filter tape, we have a rod that's typically made out of palladium or niobium, which are obviously fairly rare elements and unlikely to be present in your sample. We establish a value for those when the instrument is calibrated. And then with each and every sample, we check and make sure that the reported value for that is within plus or minus 10% of its original value at the time of calibration. And so what that means is each and every sample that you do analysis on is traceable back to the original calibration of the instrument. We also do a daily upscale check. We have a rod that has a couple different elements of interest on the end of it. It gets inserted into the analysis area once per day. It's an additional check once per day on the stability of the XRF system. And again, one of the nice features of XRF just in general as an analytical technique is that calibrations are very stable. While often we recommend doing calibrations about once per year, sometimes we have seen that users can go several years even between calibrations. The next few slides show some of the work that we've done with the instrument in the laboratory, kind of demonstrating some of the stability of the overall system. This is a test that we did over the course of 2 days, analyzing a sample with 6 different elements in it: nickel, copper, zinc, arsenic, cadmium, and lead. And basically, the instrument is just analyzing the same sample over and over again, and we're observing what the standard deviation in the reported concentrations are. And what you can see is that the standard deviation, or the relative standard deviation for most elements, is less than 1%, indicating very, very good stability in the XRF analysis over the course of the test. We've also done some work demonstrating the linear range of the instrument. As you can see, you have here 4 different elements. You have nickel, zinc, copper, and arsenic again. You have the actual concentration or known concentration of the sample on the x-axis, and then the measured concentration by the Xact on the y-axis. And what you should note is that this is a logarithmic scale. So you see samples, the lowest concentration at about 1 part per billion, while the highest concentration is about 10,000 parts per billion. The slope over these ranges is very, very close to 1 for all of these elements. The R squared is 0.99, indicating very, very good precision in that analysis. And basically what you're seeing is the ability of the instrument to make a measurement over a very wide range of concentrations without changing the calibration. And then we've also done some testing at very, very low concentrations as well to demonstrate the linearity and the accuracy of the instrument. This is a test that we actually done as part of a factory acceptance for use in a nuclear power plant application, where we compared the Xact 920 response to a known solution concentration, but at very, very low concentration levels. Here, what you're seeing is concentrations that range from less than a part per billion up to about 25 parts per billion. And for iron, copper, and lead. Again, for each element, the slope was very, very close to 1, indicating good agreement between the reported exact value and the known concentration of the solution. And then the R-squareds are 0.99 again, indicating a high degree of precision in that fit. So the next several slides will deal with some of the field testing that we have done with the unit. This field testing was done at a facility, a coal-fired power plant with flue gas desulfurization. And we were monitoring a sample of the flue gas desulfurization wastewater. This is it's kind of a schematic on this page of the treatment system that was involved in this particular facility. It had a physical chemical treatment, a clarifier, a bioreactor, and an effluent holding tank. We did quite a bit of sampling out of the effluent holding tank, which means sampling downstream of the bioreactor. And then we also did some sampling, which essentially upstream of the bioreactor, but downstream of the physical chemical treatment as well. The instrument was installed in January of 2020, was operational in just a couple of hours of being taken out of the crate, and we were able to start gathering data almost immediately. During the first part of the study, the instrument operated from January 9th of 2020 to March 13th. It had an uptime during this period of about 97, 98%. And then during the course of this operation or this study, the bioreactor started operating at about the middle of that, about February. We compared the Xact results to that of a laboratory. We used Brooks Lab in Bothell, Washington, which was recommended to us by the Electric Power Research Institute. And we had two different types of grab samples. We had analysis of the same grab sample. So in other words, you grab a sample, you put it in a bottle, and you split it in half, and the Xact analyzes what's in the bottle, and you send the other half of that bottle up to the lab. The other is a grab sample that's being collected while the Xact was operating continuously and continuously sampling the bioreactor effluent. And we had three different grab sample campaigns, one at the very beginning, one kind of in the middle at the end of January, and then one at the end of February. And then these are the results that we got from this particular test in comparison to the lab. What you can see on this table here is you have concentrations that range from about 20 parts per billion to about 150 parts per billion. And the average percent difference between what the Xact is reading and what the lab is reading is about 1.3%. So very, very good agreement between the Xact and the laboratory. And then this slide just kind of shows the same data, just in a different format. You have the exact concentration on the x-axis, the concentration from the lab analyzed by ICP and spec on the y-axis. You're seeing a slope of almost exactly 1 in an R-squared of 0.9. Again, the slope of 1 indicates almost perfect agreement between the Xact and the laboratory. The R-squared of 0.99 indicating a fairly high degree of precision in that comparison. We also did some spike recovery testing. Spike recovery testing is kind of a common way in a laboratory of evaluating the effects of any kinds of interference in measuring your analyte of interest. EPA, basically the way a spike recovery works is you make a measurement of your sample, you add a known amount of the analyte to that sample, and then you measure it again and make sure that the difference between your first measurement and your second measurement is equal to the known amount of the analyte that you added. Typically, spike recoveries are reported as a percentage, with 100% being, perfect agreement or perfect recovery of the amount that was added to the spike, or excuse me, the amount that was added to the sample. And for QA purposes, the EPA recommends for laboratories that its spike recovery is between 70 and 130%. And what you can see here for the Xact is the spike recovery is well within that range. We also did testing with it in terms of adding Selenium 6 and adding Selenium 4. And with both samples, we're seeing good agreement and good percent recoveries. We also did some very specific detection limit determinations on the Xact with the specific samples that we were doing. We're seeing samples from both the clarifier, so post physical chemical treatment, and then we're also seeing samples from the bioreactor. And what we did is we did the standard EPA procedure for determining the detection limit. We took a sample, we analyzed it 7 different times, utilized basically the standard deviation of that to get our detection limit. What we see for the outflow of the clarifier, we're seeing 3 parts per billion. For the outflow of the bioreactor, we're seeing 2.5 parts per billion. And this slide shows some of the data that we gathered while the bioreactor was operating, or the facility was operating. The gray dots you see there are the exact reported concentrations for selenium. And then the other items there you see are grab samples that were gathered. And what you can see is obviously very good agreement between the Xact and the reported ICP mass spec values for the grab samples. And then this shows something very similar. This time, the first slide shows it, the first slide shows us with an upward trend in selenium concentration, where you're starting out at a lower concentration of selenium and going up to a higher concentration. And then this shows the same type of thing, but going from a higher concentration down to a lower concentration. Again, the gray dots there are the exact 920 concentration, and the diamonds there are the ICP mass spec grab samples. I think this slide here shows the concentration of selenium over that entire operation of about 2 months, from the beginning of January to the end of March there. And what you can see is that the selenium concentration isn't necessarily stable over time. There were some high concentrations when the facility, the bioreactor, was starting up. And then, of course, as you might expect, gradually things went down lower over time. But there are some areas where you see, spikes in the selenium concentration or sudden changes in the selenium concentrations that may or may not correlate with specific facility events. And this shows some of the reasons why online monitoring might be important to a facility, to understand why these spikes are occurring, and to be able to do something about them before an exceedance takes place. We also had a second campaign, sampling campaign at the same facility. The Xact ran out of filter tape in March of 2020 and was not operated from March into July of 2020 due to site access restrictions from COVID-19. Basically, power plant obviously is a fairly important thing that has to keep running, and they didn't want anybody on site to make sure that there wasn't any issues with people getting COVID-19. The instrument restarted collecting data near the end of July, and then ran until about the end of November of 2020. We were able to gather some more data comparing the Xact to ICP mass spec. This slide here shows data from both the first study at the beginning of 2020 as well as the second study towards the end of 2020. We were able to get some lower concentration data, so that was nice. Some of the concentration data on this plot here is less than 10 parts per billion. Again, with this additional data, you're still seeing very good agreement between the Xact and the laboratory method. You're seeing a slope of 0.98 and R squared of just about 0.99. Again, indicating perfect agreement, so very close to perfect agreement between the Xact and the laboratory method. And then the R squared indicating a very high degree of precision in that comparison. And then at the end of the study, we were also able to do some work sampling back and forth. As I mentioned, we were able to sample downstream of both the clarifier and downstream of the bioreactor. And this shows some of the data switching back and forth between those two locations. Obviously, the downstream of the clarifier you're seeing there in green with a little bit higher concentration. That's essentially the influent to the bioreactor. And then the blue dots there are the effluent from the bioreactor, which, as you might expect, show lower concentrations. During this particular study, we had to switch back manually, but at this point in time, we have automated sampling stream switching available on the instrument. So in conclusion, the real-time data from the Xact can provide useful feedback for plants that are trying to comply with regulatory limits, specifically the regulatory limits associated with the ELG rule. Consistent monitoring can provide data to improve your treatment efficiency and to understand why you have deviations and changes in your selenium concentrations. And the Xact provides data that is accurate, reliable, and compares well with independent laboratory analysis. It's also very easy to install and operates very reliably. And I think with that, I will go ahead and stop sharing my screen and see if there's any questions that are present in the chat box. Please let me know if you have any questions, and feel free to write your questions in the chat box there. We'll try to answer them as we can. I'll wait a couple minutes for folks to write in their questions, and if we don't see any, then we'll go ahead. I do see a question from James. It says, do they still have to do lab tests, or can they use this for compliance? So at this point in time, the Xact is not a compliance instrument for meeting the ELG rules. It's more being used as a process control tool rather than as a compliance tool, and facilities still have to do laboratory analysis. My understanding is that it is possible to get EPA compliance or EPA certification on the instrument, but that's not something that we have pursued at this time. So so he asks again, so it helps them avoid fines with continuous monitoring. Yes, that is correct. That is one of the major reasons why you would want to use the instrument, is to prevent the facility from being fined for an exceedance on their laboratory or their manual sampling. It's also helpful in terms of understanding how to make your treatment process more efficient. There are chemicals and things that you have to add to the treatment process, food that you have to give to the bugs there in the bioreactor to make them live, that it's helpful to understand how to make those work more efficiently so that you're not spending as much money on those particular things. So somebody asked, the unit should be installed in a cabinet or shelter. How far from the source can it be? It should be pointed out that the unit actually comes in a small temperature controlled, and I guess maybe not small, but it comes in a temperature controlled enclosure. It's roughly the size of a refrigerator, I would say, a large, like, commercial refrigerator. That cabinet is temperature controlled. It has an AC on it. It's a NEMA 4 cabinet, so you know, it can get wet. It can be sprayed and hosed off, all of that stuff. So there's no need for it to be put in a shelter. In terms of how far it can be away from the source, I would say somewhere around maybe 30 meters or so. We have a fast sample loop, as I mentioned, that will pull a sample from the source at a rate of about 1 liter a minute. And so what that does is that makes sure that there isn't a large amount of lag time between when you're sampling from the source and when it is actually sampled on the instrument. So that would be kind of, I guess maybe that would probably be the limitation, is how much lag time are you willing to live with between when the instrument samples the source and when that value is actually reported or sampled on the instrument. We'll wait a few minutes to see if there's any additional questions from anyone. I'll also put my email in the chat box here. If anyone here has questions that they'd like to send us after the presentation, please feel free to do so. My email is right there. It's craigp@sci-monitoring.com. Please, by all means, feel free to email me your questions, and we'd be happy to answer those. I think I'll wait just a couple more minutes to see if there's any additional questions, and then we'll sign off. Somebody asked if the data can be sent by internet I guess offline. Yes, it can. In terms of the data, there's a couple different methods for getting the data. The data can be grabbed off of the instrument itself, obviously, as a comma delimited text file. It can be, there's an RS-232 port available, so an RS-232 serial port, and then the instrument data can be gotten via a Modbus protocol. The Modbus protocol is also available over TCP/IP as well. And it is also possible to have a script program on the PC that will push data via the Ethernet connection to a location of your choosing. It's also important to point out that almost all of the instrument's operations can be performed remotely via the internet as well, and a remote desktop application. So the instrument computer is essentially a PC, and you can log on to that PC using remote desktop or TeamViewer, and utilize any of the functions that are available on the software remotely from your PC. I think this also kind of brings up some things in terms of maintenance. The Xact, the filter tape needs to be changed. Typically, if you're using the instrument in 1 hour mode, so if your sampling and analysis periods are 1 hour long, the filter tape will last a month. The other consumable that we see used is, as you may recall, we have a liquid blending module, and we utilize an internal standard. So there is a solution that's about a 2 liter bottle. That 2 liter bottle will last you a month as well. So what you can expect in terms of interaction with the instrument is changing the filter tape and changing that bottle once a month. Those procedures should take about 10 minutes. Okay. Well, I certainly thank you all for your attendance today. Like I said, if you have any additional questions that you think of later that you'd like, please email them to me at the email that I put in the chat box there, craigp@sci-monitoring.com. Thank you all for your time and your attention.